All right, welcome everyone. We'll give everybody a second to kind of roll in here for today's presentation. The numbers just keep going up. We had a lot of you registered, so definitely a lot of interest and excitement about this online. So we're really happy to see you all joining us. So I'm going to give everyone a second to get on, get logged in, get comfortable. Today's presentation will be an hour, so you may or may not need a snack. We always get a lot of questions of how long is this? Today we'll go from 2 to 3, just to kind of give you a little heads up there. All right. So, hello everyone. Thank you so much for joining us for the 5th installment of LBDA's 2023 Community Webinar Series. Today's program is entitled Understanding the Science Behind Disease-Modifying Trials in Dementia with Lewy Bodies. My name is Julia Wood. I'm the Director of Professional and Community Education here at the Lewy Body Dementia Association. And just so you know, throughout the remainder of 2023, we're going to continue to host this series of webinars on a variety of topics for people living with Lewy, your care partners, your community members, your family and friends. So far, if you've been tuning in, we have addressed cognitive and vision symptoms, and we've learned strategies for managing care from the International Neuropalliative Care Society, and also Brandy Hackett, LBDA Senior Manager of Support Services. Today, we're going to switch gears a little bit and focus on the amazing efforts going on at LBDA in research, and also some exciting scientific advances that are happening in the dementia with Lewy body space. So to host our program today, I thought there would be no one better than my colleague, Dr. Keith Fargo. And Keith is LBDA's Director of Scientific Initiatives. And so please use your icons down on the bottom. You can use your reactions and give a warm welcome to Dr. Fargo. Welcome, Keith. And Keith, you're on mute.
Thank you very much, Julia. Thank you for the introduction, and welcome to all of you for joining us today. Before I introduce our speaker, though, I'm going to tell you a little bit more about LBDA. The Lewy Body Dementia Association is a 501c3 national nonprofit organization, and we were founded 20 years ago by care partners and family members who were seeking support and answers to their questions about LBD. Our mission is dedicated to advancing awareness, research, education, and support for individuals and families who are living with LBD. To learn more about how we can help, please visit our website, lbda.org. A few housekeeping items before we get started. First of all, as Julia mentioned, you are absolutely welcome and encouraged to please submit questions anytime, not just at the end, but anytime throughout the presentation, by typing them into the Q&A button on the bottom of the screen. Well, not into the button, but you click the button and that opens a box for you to type into. Following the presentation, our presenter today will answer your questions for approximately 10 minutes. And this presentation is being recorded, and an email will be sent to those who registered in about 1 week. That will contain a link to the recording. Also, when you exit the webinar today, a brief survey will appear asking for your feedback about today's presentation. Please do take a moment to fill that out because it really helps us inform our content for the future. LBDA is delighted to bring you this webinar today. As you know, unfortunately, there are few treatment options available for people with LBD today. But in recent years, there's been an increase in the number of clinical trials for dementia with Lewy bodies, or DLB, which, along with Parkinson's disease dementia, PDD, is our focus. Most of the recent growth in DLB trials examine what we call disease-modifying therapeutics. That is, therapeutics aimed at slowing, stopping, or preventing the underlying disease process in the brain, rather than simply alleviating symptoms for a period of time. The research that you're going to hear about today is being conducted at LBDA research centers of excellence across the country, in addition to other clinics. You can visit our website, lbda.org, to learn more about these studies, find a study location near you or your loved one, and learn more about the research centers of excellence. You may also wish to sign up for Lewy Trial Track. This is an LBDA service that allows us to provide you with information about clinical trials that match your interests. This is also done through our website. Just log on or just visit the website and search for Lewy Trial Tracker. And now I would like to introduce our presenter, Dr. James Galvin. Dr. Galvin is nothing less than a leading light in the field of LBD research and care. Dr. Galvin is professor of neurology and psychiatry at the University of Miami Miller School of Medicine. He's also the founding director of the Comprehensive Center for Brain Health, the director and principal investigator of the Lewy Body Dementia Association Research Center of Excellence at Miami, and chief of cognitive neurology for Palm Beach and Broward County, Florida. Dr. Galvin has authored over 300 scientific publications and 3 textbooks on healthy brain aging, cognitive health, Lewy body dementia, and related disorders. Please join me in welcoming Dr. Galvin.
Well, thank you, Keith, and welcome everybody to our chat. So I thought over the next 6 or 7 hours, we could cover some of the great research advances. That was a joke, 6 or 7 hours in Lewy body dementias. And so I think I just want to get started. I'm going to try to talk for about 30 minutes to 40 minutes so I can leave plenty of time for questions. Okay. Now, if everything cooperates, I will share my screen right now. All right. So here's our title. We're going to try to understand some of the science behind that. And so our objectives for today are to define alpha-synuclein and beta-amyloid protein. So when we talk about disease modification, I think it's important to know what we're actually modifying. So we'll talk a little bit about this. We'll define how alpha-synuclein and amyloid beta protein may play a role in brain changes associated with dementia with Lewy bodies. And then we'll try to summarize some of the potential benefits of targeting these proteins for people living with DLB. All right, so both Alzheimer's and DLB are neurodegenerative diseases. So these are progressive diseases that are associated with neuronal or brain cell changes that occur. And as part of this degeneration, there's also the accumulation of abnormal proteins. So we can see on this slide a couple of sections of the brain. And so in the first row are some sections from a part of the brain called the midbrain. And it's part of the brain stem. And this is the substantia nigra. So I'm going to show you in this slide right here, the healthy control. See this dark line right here. This dark line are where many of the dopamine neurons are located in the brain. Dopamine is important for a lot of things, but 2 of the things it's particularly important for, one is for movement. So if these cells die and degenerate, then a person will have trouble moving, and they'll develop the signs of Parkinson's disease. Another important aspect of dopamine, it's important for sort of our motivation and some of our behaviors. So our impulses, our sense of reward. So if we do something and we get rewarded for it, either a monetary reward or a pat on the back, dopamine is released that makes us feel good about ourselves. So dopamine has both a motor function as well as a behavioral function. And in Lewy body dementia, there's a loss of these neurons. So there's a dopamine depletion. So if you look at the brain of a person who has a healthy control, you see this nice dark line. And you look at a person who has Alzheimer's disease, again, you see that nice dark line. But in a person with dementia with Lewy bodies, you can see that dark line now has faded. So these cells have died. Okay. If we go down here, this is the temporal lobe. And so the temporal lobe is, right about here in the brain. And this little seahorse-shaped structure is called the hippocampus, which means seahorse. And so this is an important area for the short-term memory aspects of the brain. So this is how memories get in and get coded. and then stored so that you can access them later. So it's important for learning and memory. And you see in a healthy control, you have a nice looking seahorse. But you see in Alzheimer's disease, this seahorse is smaller, it's shrunken, and the space above it is dilated. So there's hippocampal loss in Alzheimer's disease. What's interesting is if you look at the brain of people with dementia with Lewy bodies, even though they do have a bit of a memory problem, there's much less loss of this hippocampal structure. So not only are the symptoms a little bit different, but the parts of the brain affected are very different between the two disorders. On the slides next to it, we have microscopic sections of the brain, and this shows you the pictures of the Lewy body, which is the abnormal deposit of protein in the brain of people who have Parkinson's disease and dementia with Lewy bodies. So here in A, we can see the circle, and there's a little dense core with a pale halo. And so this is a Lewy body, and this is what Dr. Lewy described back in the early 1900s. And it was very hard to see. Right below it is a Lewy body in the cortex, or the gray matter of the brain. And this wasn't described until 1961 by Dr. Okazaki. And the reason there was almost a 50-year gap between the two is that it really doesn't look the same. It's kind of hard to see. There's not the nice, clear, round shape without the halo and the core. So it's very, very difficult to make these diagnoses. But today we have antibodies. So these are specialized stains that allow us to see the Lewy bodies on sections. And so now using stains, these Lewy bodies now pop out. And so it's much easier for us to make this diagnosis in life, after life. What's important about it, though, is that these same Lewy bodies are caused by a protein called alpha-synuclein, and we're beginning to develop methods that we can now look at alpha-synuclein in living individuals, either through spinal fluid or through skin biopsies. So it's really changing the way we're going to be making diagnoses going forward. Similarly, there are changes on imaging studies. So just as I showed you those changes on the brain sections, obviously we have to wait till someone dies to look at their brain, but now we have imaging studies that allow us to look at this. So again, if we look at an MRI of a person with dementia with Lewy bodies versus a person with Alzheimer's disease, there's shrinkage in the brain on both cases. But remember that hippocampus, that seahorse-shaped structure, it looks a lot better preserved in a dementia with Lewy body case than it does in an Alzheimer case. So we can use imaging studies to help us discriminate between the two causes. I talked about dopamine, and we don't have to wait to look at someone's brain to see this. We can actually image dopamine in a living person, and this is called a DAT scan, or a dopamine transporter scan. So you can see in a healthy control, you see this comma-shaped structure. This is the basal ganglia. It's part of the brain that helps us initiate and start and smooth movements. And so what we can see is this comma-shaped structure. This is the caudate and the putamen. That's two parts of the basal ganglia. But in a person with Lewy body dementia, you can see now it no longer looks like a comma. It looks more like a period. So we've lost that putamen structure. And so that's diagnostic of a person with Parkinson's or dementia with Lewy bodies. And then I won't talk about this very much, but we also have specialized scans looking at the heart that can tell us these things as well. So we're developing many, many tools that help us make diagnoses of DLB in living individuals. Now, I mentioned we're going to talk also about beta amyloid. This is the protein that's abnormal in Alzheimer's disease. But roughly 80% of patients who have DLB also have Alzheimer changes in their brain. And roughly 30% of patients who have Alzheimer's disease have Lewy body changes in their brain. So there's a tremendous overlap between the two disorders, which makes it, one, hard to diagnose, and two, more importantly with this talk, is that certain therapies, depending on what protein abnormality they're targeting, could potentially benefit both patients with dementia with Lewy bodies and patients with Alzheimer's disease. So this is a very exciting and interesting ongoing area of investigation. So what I want to show here is this structure here, which is the plaque, the senile plaque in Alzheimer's disease. And this is a deposit of amyloid protein. So we can see it on one type of stain here. And if we look down at this slide over here, down on the box that says E, This is a silver stain. We can see this amyloid plaque very well. Okay. The other thing that happens in the brains of both patients with Alzheimer's and to a lesser extent in patients with Lewy body dementia is deposits of another protein called tau, which makes the tangle. Okay. And we'll talk about why that might be important to know about as we move through our talk. Okay. So we talked about alpha-synuclein. This is the building block for the Lewy body. We talked about beta amyloid. This is the building block for the senile plaque. 80% of DLB patients have both Lewy bodies and plaque. 30% of Alzheimer patients have both plaques and Lewy bodies. And then there's another protein sort of off to the side that's not the main focus of our talk, called the tau protein, which deposits as a tangle. And there are many, many more tangles in Alzheimer's disease than there are in Lewy body dementias. But we'll talk about why the tau still may be important to consider. Okay? All right. So with that as a backdrop, that's the proteins and how we use the proteins to help us in pathology after an autopsy, discriminate between the two disorders, and how we may be able to use this going forward in living individuals. Okay. Now, let's talk a little bit about clinical trials. When we're giving medications, there are really two ways that medicines can work. Well, there are many, many ways medicines can work, but for the purpose of this talk, there are really two ways. One could be symptomatic benefit. That is, the medication treats a symptom, but doesn't take care of the underlying problem. Or it could be a disease-modifying medicine. That is, it takes care of the underlying problem and may or may not have a benefit on symptoms. And so we can design studies to try to look at these differences. So I don't want to go really heavy into study design, but there are ways for us to tell things, and we look at the patterns. So this is a case where we start someone on drug. So there's a person in the active arm, they're getting the drug, and there's a person in the placebo arm, they're not getting the drug. Then after a certain period of time, we take away the drugs from the people in the active arm, and we see what happens. And so there are two things that can two types of patterns that can happen. So the first, if it's a symptomatic medicine, you take away the medicine and any benefit the patient had is immediately lost because you weren't addressing the disease, you were just taking care of the symptom at the moment. So you can think about that as like taking cough syrup, right? Cough syrup doesn't treat your flu, it just suppresses your cough. If you stop taking the cough medicine, you'll go right back to coughing, okay? And so what we can see is that for the people who had symptomatic benefit, they immediately sort of decline and head toward that group that was never treated before. That's a symptomatic benefit, okay? If we've changed the disease in some way and we stop the medication, then what we see is the group decline sort of in a parallel way to the placebo group, but never approaches the placebo group. And that tells us that in some way we've modified the disease, okay? The disease is now different because we gave this particular type of medicine. The other type of design that is something called a staggered start, so that we give the active arm and the placebo arm, and again, at the end of, say, 6 months, for example, the two groups are different. Then instead of taking away the medicine from the person in the active arm, we give the medicine to the person who is in the placebo arm, and we see what happens. And so again, if it's a symptomatic benefit, the placebo group will immediately show a bump up toward the active arm because we're treating those symptoms now that weren't being treated before. And for the disease-modifying type of effect, again, you can see that the placebo changes the slope of its decline and parallels the active group, okay? Now, this is a schematic. In real clinical trials, it never looks this clean. But knowing what these patterns are can kind of help us understand, okay? And one last point I want to make is that I'm going to talk about disease-modifying medicines going forward, but I want to make it clear to everybody, there's always going to be a need for a symptomatic medicine, and there are a number of trials going on to develop a better symptomatic medicines than what we have now, okay? So just sort of showing those same kind of curves again, So we have someone who's declining, we give them a symptomatic medicine, they get a little bump, but the disease is still progressing. So what happens is they get a benefit compared to people who never took the medicine, but they still decline. Okay. If we were to give a disease modifying medicine alone, right, this is what would happen if we did nothing. And if we modify the disease, we've changed that slope. Okay, we've changed the way they're progressing, but they were having symptoms all along. And so they'll continue to have symptoms. So the way that we currently treat people is thinking about combining these two, right? So that if we have a disease modifying medicine that we could slow down or halt the progression of disease and then give a symptomatic medicine, we would get a multiplicative benefit, right? It would be greater than the effects of either one by themselves, okay? So we're going to talk about disease modifying medicines, but there's always a need for symptomatic medicines, right? Because they do work. So this is some data, old data from Alzheimer's disease. And these are medicines that you probably have heard of: donepezil, which used to be called Aricept, rivastigmine, which used to be called Exelon, and galantamine, which used to be called Razidine. And if you look at the treated group versus the black line, which is the placebo group, for cognition, for global abilities, for function, for behavior, it's always the same. If you get someone to a therapeutic dose of a symptomatic medicine, they're doing symptomatically better than the person on the placebo. Okay? And we have lots of evidence and models of using combination therapy. So this is a combination therapy, again, in Alzheimer's disease, using memantine, which used to be called Namenda, and donepezil or Aricept together. And again, if you look at the people who are on the placebo group and they're just getting a symptomatic medicine versus people who are taking both, combination therapy gives you a more robust symptomatic response. Okay, so again, I want you to keep in the back of your minds, we talk about disease modifying medicine, there's always a reason to use symptomatic medicines as well. All right, let's talk a little bit about amyloid beta protein first, and then we'll move to synuclein, because we know a lot more about amyloid beta protein. So amyloid beta protein is part of a larger protein called the amyloid precursor protein, or APP. Okay, this is a protein that's found in all cells, and it's a transmembrane protein, right? Which means it goes across the cell membrane. So some of it sticks out on the outside of the cell, and some of it sticks out on the inside of the cell. And so there's this big molecule, but you see there's a little piece of it right here, which is really the amyloid beta protein, and it's always there. And because it's there, it has a function, which we don't fully understand, but it has a normal function. And because it has a normal function, then there must be ways of getting to it. And so there are enzymes available. And so they're called secretases. So you have an alpha secretase that clips it right in the middle of the amyloid beta protein and gives you a bunch of particles, but none of them can cause Alzheimer's disease. Okay. And then there's another pathway called the beta secretase pathway, which clips the top part of the APP protein, and then a gamma secretase that clips the bottom part, and this releases amyloid beta protein into the space. And amyloid protein is sticky, so it likes to find other amyloid beta proteins, and it builds up a plaque. Okay, so that's basically how a plaque forms. And again, it's really much more complicated than this little cartoon, but I think for the purposes of our talk, it covers what we need to think about. So there are lots of anti-amyloid therapies that are being tested, and some of them are approved, right? So again, what we know is that amyloid builds up probably first, years before people are symptomatic. So even at the asymptomatic stage, amyloid increases. Remember that protein tau we talked about? That also increases in the Alzheimer brain. And as tau increases, people develop symptoms. So they go from being asymptomatic to having mild cognitive impairment to having Alzheimer's disease. Okay. And again, I showed you that little cartoon is a slightly different cartoon. We clip away the amyloid, it floats, it tries to find friends. So monomers, which is a single component, then finds a bunch of other monomers and it forms an oligomer, a clump. That oligomer then starts to form a shape called a protofibril, and then eventually a fibril. And that fibril eventually forms the plaque. Okay? And the plaque is damaging to the brain cell. There are antibodies that have been tested that attack different parts of this pathway. Okay? And what we have approved is aducanumab, right, which attacks down here in the earlier phases, the oligomers. That was approved in 2021. Lecanemab, that was approved in 2023. This attacks largely the protofibrils. And then late-stage investigational, so they finished their phase 3, was donanemab, and this attacks the fully formed plaque. So these different antibodies attack the molecules at different spots. So they're all going to give slightly different effects. So if we look at the effects of those anti-amyloid antibodies, in aducanumab, if you look at the placebo line versus the high dose, there was a 71% decrease in the amyloid in the brain. So it effectively is removing amyloid from the brain. We see that's true for lecanemab and for donanemab as well. And in fact, matter of fact, donanemab is so effective at removing the amyloid from the brain that in the clinical trial, they actually stopped giving the donanemab and switched the people to placebos because the amyloid was essentially gone from the brain. Okay, so it's very, very exciting. It allows us to start to think about this in ways that, well, how could we most benefit patients from starting early therapy? So again, if we look at sort of anti-amyloid therapies, they attack all the different, there's many other drugs out there besides the monoclonal antibodies, which again, we're not going to have time to talk about, that can affect each part of this pathway. Okay. But what's really clear, again, not only does it remove amyloid, but it actually has clinical benefits. So this is just one piece of data from each of those antibody studies. So in aducanumab, the high dose people showed much less change in their cognitive function. Okay, so you can see here. And if you look carefully, if you remember back to that picture I showed you, this is almost parallel to the placebo group. Okay, not quite, but almost parallel, which goes along with this concept of disease modification. If you look at, this is donanemab, here is the change in the amyloid in the brain, and you can see it, no change for the placebo and a dramatic change for donanemab. In Clarity AD, which is the lecanemab trial, I know they all sound the same, but anything that ends in MAB stands for monoclonal antibody. Again, if you look at the change over time, here's the placebo group and here's the high dose group, and you can see again, they're almost parallel to each other. Okay, so again, that gives us evidence of support of a disease modification. I could show you lots of other data. And again, I don't want to drive home the point too much, but the fact is that these antibodies are very effective at removing amyloid. Why am I spending so much time on Alzheimer's disease? It's because it lends itself for a very good model for how we're attacking Lewy body dementias in the medicines or the trials I'm going to show you next. And what we kind of know is how much do you actually have to remove to get an effect? Well, aducanumab had a relatively small clinical effect. It removed amyloid, but it had a relatively small clinical effect because it was much less effective at removing amyloid than lecanemab or donanemab. So this suggests that you have to remove a certain amount of these proteins in order to get a true disease modification. Okay, so we learned from aducanumab that is it enough to just remove some amyloid? Probably not. From the lecanemab, we can see, again, much more effective removal of amyloid, and we get a bigger effect, a 27% slowing of disease in people who were treated. So there's disease modification, but this also has some symptomatic benefits. So we're getting a little bit of best of both worlds. And we see something even potentially more robust in donanemab because it's much more effective in removing amyloid than the other medications. Okay, so removing proteins is important, it does provide some disease modification, and that shows itself in some clinical benefits. Now, there are lots of medicines out there, right? So many that you will probably have trouble saying because some of the names right now are really, really challenging. But I just want to show you that it's not just amyloid out there, right? So for Alzheimer's disease, it's not just amyloid. There are anti-tau medications, there are neuroprotection drugs, there are things that work at inflammation and metabolism, and then other targets that don't fit nicely into any one little bucket. And so hundreds and hundreds of medications are being tested out there. And we know a lot about this, right? And so we've learned a lot from the Alzheimer field that we're now going to switch over to the dementia with Lewy body field and how we're applying that learned knowledge going forward. So there are no currently approved medications for dementia with Lewy bodies in the United States. There is in Japan, but not in the United States. So what we do is we borrow medicines from other fields right now, so we can treat the cognitive symptoms, the motor symptoms, the fluctuations, the behaviors, the sleep, and we use medicines for other diseases. But if we look at the data, and this is some data from Parkinson's disease dementia, pretty much we can see that the cholinesterase inhibitors that have been used since the 1990s can be quite effective symptomatic treatments for DLB. We have lots of options available to us, and we have fairly good evidence that they may actually help anecdotally, but in clinical trials, it's often really hard to establish this. So even though I said we borrow all these medicines, the fact is we don't have a lot of really good randomized clinical trials with these symptomatic medicines. So what's been really interesting in the last couple of years are trials ongoing to actually test potentially disease-modifying medicines. So let me show you one that was completed. This was a study by a company called ASI, and the drug is E2027, or isonitrotine. And so this inhibits a chemical that increases some of the messaging signals inside a cell, cyclic GMP. Don't have to worry about cyclic GMP. But the fact is it may help protect synapses or the chemical connections between cells. And so the idea was that this drug, by increasing the amount of this messenger system, would help improve cognition in patients with DLB. And so there were 83 people screened and 34 people enrolled. So a very small study. And what we initially found was that there was no effect. So it was the trial failed to reach its primary outcomes. What was interesting, though, is that in sub-analyses, people with the lowest amount of amyloid actually had the best response. So that the two pathologies together probably limited the benefit of this medication, right? And that's important because, as I mentioned, 80% of DLB patients also have amyloid, and 30% of Alzheimer patients also have synuclein or Lewy bodies. So the proteins may be interacting in ways that we have to really think about how we're going to do this. And so there are two basic strategies to do this. One, we could not test or exclude people who have these other proteins from clinical trials, but that may not represent the whole group. Or we could try to design medicines that work on more than one protein, and that may help. So I'm going to show you some examples of those two strategies. So before I do that, just one last thing. There's lots of really cool things happening. And not only are new drugs being developed, but old drugs are being repurposed. Okay. So this was a paper that came out last year where they looked at all the evidence for these existing medicines. They're used for other things. And Broxol is a mucolytic. It helps break up phlegm. But it may be a very powerful drug for treatment of Lewy body dementia. Metformin is a drug for diabetes, but it may have some effect in Lewy body dementia. So these are all being tested now. All right, so let's go to some clinical trials. So the first I want to talk about is a compound called CT1812. And so this is a study in mild to moderate dementia with Lewy bodies. It was awarded by a grant by the National Institutes of Aging to Cognition Therapeutics and myself. And so this is a first-in-class small molecule, okay? It works at a receptor called the sigma-2 receptor. But what's important is it seemed to selectively displace or block the ability of both amyloid beta protein and alpha-synuclein to bind to brain cells. So it seems to protect the synapse, those important connections between cells, that's how they communicate, seems to protect the synapse from the toxic effects of these amyloid and synuclein proteins. Okay, so this is a study that's ongoing right now, a phase 2 study in 120 sites. So I have this little cartoon here, and so the synapse is basically the connections between one cell and another cell. Now they don't actually touch. There's a gap, and this gap is chemical transmission going back and forth. So if we blow this picture up here, there are receptors here where the oligomers, those clumps of protein, can bind to and cause cell damage. Okay, the sigma-2 receptor is part of that complex that binds the oligomer, right? So by acting at that sigma-2 receptor, you can block the ability of those oligomers to bind to cells. So I'll show you some pictures. So this is a cell culture. So these are cells that are grown on a plate. And so we can see that this one has lots of little synuclein oligomers, all these red dots, okay? And they're binding to the cell. And if we treat the cells with CT1812, then we can displace those little synuclein oligomers from the cell, and that potentially can protect it. And we can demonstrate this when we use looking at the plasma of people who had Parkinson's disease, and we can see that we can change sort of the trafficking of the proteins through the cell, right? So it can have very beneficial effect by modulating this particular receptor. So where are we with this study? 120 people we're looking for in 30 to 40 centers across the US, and we're testing 2 doses, a low dose, 100 milligrams, and a higher dose, 300 milligrams, against a placebo. There's 40 people in each arm. So it's a 1-to-1-to-1 randomization. So if you're in the trial, you have a 66% chance of being on drug. Okay. The primary thing we look for in an early study is safety and tolerability, but we're also looking and seeing whether it works, whether there's efficacy. So we're measuring cognition in a couple of different ways, both pencil and paper and computerized test. We're looking at symptoms, so fluctuations, sleepiness, Parkinson motor features, their overall global abilities, their activities of daily living, their behaviors. So we're capturing all this. And we're also looking to see if we can actually change the amount of synuclein, that's the building block of Lewy bodies, pathology in skin, okay? Because that we can get to very easy through a skin biopsy. So this trial is looking for people 50 to 85 with probable DLB, and they're allowed to be on a stable dose of their symptomatic medicine. And so they have to be in the mild to moderate stage. So we have a screening test called the mini mental state exam, and this is the mild to moderate range. For exclusion, you can't have a diagnosis other than DLB. People who are actively depressed are not eligible. People who are not living in their own homes are not eligible because we need a regular caregiver. And there are other things that we typically exclude people for in clinical trials that I won't go through here. So to date, we randomized the first person back last June. We've screened over 121 people with more people in the pipeline. 13 of the sites are from the Lewy Body Dementia Research Center of Excellence programs. So we expect to finish enrollment in this study by the end of the first quarter of 2024, which means we hope to have a readout of the study, by the summer or fall of 2024. So not that much, less than a year from now, we should have a readout from this study. So we're really excited about this. There are some challenges that we've overcome. And again, I'm not going to dwell on these things, but anytime you do a study, there are lots of tricks to getting this done. I want to mention another study. This is called Rewind Lewy Body, or Rewind LB. This is a compound developed by EIP Pharma, neflamepipod, And so this was also a grant from NIH to EIP Farmer and myself. And this is also a first-in-class molecule. And this is a specific inhibitor of a enzyme inside a cell. It's called a kinase. And this may protect those cells in the brain that make acetylcholine. Okay, so it's a neuroprotective study. So this is a phase 2B study in 160 individuals. Why is it a phase 2B? Because it's the second phase 2 study that was done. This was the phase 2A study, the Ascend LB. So this was a shorter study, 16 weeks, looking at cognition and safety. And what they found was that there were benefits on global cognition and movement, but in particular, which was really important, is that if we looked at people who had more Alzheimer pathology, they were less responsive to this medicine than the people who had less Alzheimer pathology. Okay, so remember I said there are two ways of designing these disease-modifying trials, right? One, the drug might work on multiple proteins, or two, you want to select the right patient who's most likely to benefit from the medication. So in this case, for this trial, the phase 2B, we're selecting the people who have the low Alzheimer pathology because they're going to be much more likely to respond. So we're able to enrich the strategy to recruit people. So 160 people, we have the same type of outcomes. They're slightly different, but the same types of outcomes, both global and cognitive outcomes, along with safety, roughly the same sort of age groups. But this time we have this exclusion for too much Alzheimer pathology. We can measure this in blood. To date, we randomized the first person last month in August of 2023. We have had a number of people screened. There have been some failures, and it's due to this elevated phospho-tau, this elevated Alzheimer protein. So we're much more likely to be able to see things, right? And we hope to finish this trial sometime toward the end of March 2024, also looking for a readout in the fall of 2024. So fall of 2024 is going to be a really exciting time in Lewy body dementia, okay? In the last minute, I just want to say some other things that are happening. So this is another study that hopefully we're waiting to hear our award notice. So this is a vaccine, and this is a prevention vaccine. And I'm not going to go through all the science. I just want to say that there's lots of really cool things happening. So there are drugs that are being repurposed. There are drugs that are neuroprotective and disease modifying. And there's also some things being developed that potentially could prevent disease. And this is an example of that. So this was done in cells and in mice, and it was able to sort of reverse the deficits and improve both cognition and motor speed. And when we looked at the brains of those mice, the vehicle is sort of placebo, and the compound here is the vaccine. And these are the abnormal dots. These are Lewy body-like structures, and you can see there's a lot less of them if we treat the mouse. So very excited about this. Right, so to summarize, dementia with Lewy bodies is a common cause of dementia for which there are no approved treatments in the US. In order to develop treatments, we need to design better studies, design and develop specific biomarkers and specific outcomes. To date, a lot of the phase 2 studies have failed to meet their primary outcome, but I think we've learned a lot from those studies as to how to design better studies, and those really exciting approaches are currently in clinical trial, right? So CT1812, right, is a sigma-2 receptor. It works on both amyloid and synuclein. Neflamapimod is a kinase inhibitor. It's neuroprotective for those cells that make acetylcholine in the brain, but is probably going to be most effective if there's not a lot of Alzheimer pathology. So two different strategies, but both disease modifying and very powerful. Then I just showed you a little snippet of a vaccine trial to try to prevent people from ever developing the disease, right? But all the things we talked about, really, the focus is on developing disease modifying medications. And of course, if that doesn't work, then we can just go to our local store. We can buy some brain gum because, you know, that's going to work. I'm kidding. Of course, that's not going to work. So I'm going to end right here, and I'm happy to take any questions. I left 20 minutes for questions. So thank you for your attention.
Great. Thanks very much, Dr. Galvin. This is Keith Fargo. Do you mind just stopping sharing your presentation so that, yep, thank you. So we do have a number of participants with their hands raised, but if you do have questions, please go ahead and type those into the Q&A. That's really the best way for us to receive those questions and make sure they get asked and answered. Some of the questions that came, we got a tremendous number of questions coming in. We'll try to get through as many as we can. There were several asking about how to find. So before I turn some questions over for Jim, there were several questions about how to find locations where people can participate in these trials and others. So I'll just let you know that if you go to the LBDA website, lbda.org, you should be able to find up in the top, the website, there's a navigation bar. If you just click on research, that will take you to a number of resources relevant for clinical trials, including a list of the clinical trials that are recruiting today and the locations at which those trials are happening, and the name and contact information for the person working at that location who you can reach out to get more information about the study. And then, of course, I'll also mention again, Lewy Trial Tracker. This is a tool from our website that you can sign up for that will allow us to send you information about new trials that match your interests when they launch. So that way you don't have to keep checking on your own. And now we've got some questions I'd like to send over to Dr. Galvin. So the first one is, I've been told that LBD may be present for years or even decades before symptoms show. Is this true?
So these diseases begin before we know that they begin. So the changes have to occur in the brain to a sufficient amount in order for a symptom to develop. So what we know from diseases like Alzheimer's disease is that amyloid deposits can occur up to 20 years before people have symptoms. And then they develop mild symptoms as other changes occur in the brain. This is probably also true in Lewy body dementia, is that the abnormal protein, the alpha-synuclein, forms Lewy bodies, and there's cell changes, and these probably occur years before. And so that's why there is some subtle signs. So for example, REM sleep behavior disorder is a symptom that many times will develop either Parkinson's disease or dementia with Lewy bodies. And that begins 20 years or so before the rest of the symptoms begin. But if people die with REM sleep behavior disorder and we look at their brain, many of them do have Lewy bodies in their brain. So yes, it does occur before we know it occurs.
Great, thank you. The next question here is, how do we know in a living person whether they have amyloid present in the brain? And similarly, how do we know in a living person whether they have alpha-synuclein present in the brain?
Right, so we have tests called biomarkers, right? And so these are ways that we can access the brain in different ways to measure these proteins. So for amyloid, there are 3 ways that we can do this. One is through a PET scan. This is a nuclear medicine scan. And so it's done in radiology. And so there's an injection done. The compound binds to the amyloid in the brain, and we can take a picture of this, and then we know whether amyloid's present or not. The second is through a spinal tap. So the spinal fluid bathes the brain, and so whatever happening in the brain is also going to be seen in the spinal fluid. And so we can measure amyloid protein and tau protein in the spinal fluid. And the third is the newest way, which is blood. And so the blood tests are available that allow us to measure amyloid and sometimes tau as well in the blood. These are sort of kind of ready for prime time, not quite 100% there, but they are available and you can get them. So there are 3 ways we can measure amyloid. There are 2 ways we can measure synuclein right now. One is through spinal fluid, so a spinal tap, and the other is through a skin biopsy. And so in the spinal tap, we can't really measure synuclein directly, but we do something called a seeding study. So it's very sticky. So we can do a process to see how much aggregation or clumping there is of synuclein. And if it's present, then that tells us there's Lewy bodies there. And the skin biopsy, we can directly visualize the synuclein deposits in the nerves of the skin. So there are 2 ways we can see in a living person synuclein, and 3 ways we can see amyloid.
Great, thank you. So we had several questions related to causation and genetics. So rather than me reading each of those, could you just tell us a little bit about genetic risk for LBD and whether there might be any clues from the genetics for new disease-modifying therapeutics?
Right. For the most part, these diseases, all dementias are sporadic, right? That is, they occur randomly in the population. There are a few core causes of familial forms of disease. They're rare for Alzheimer's disease. They're even rarer for dementia with Lewy bodies. But there are a bunch of genes that we know increase the risk, right? So, for example, in European descendants for Alzheimer's disease, the ApoE gene is the strongest genetic risk factor. Risk does not mean cause. Risk just puts someone at a higher chance of developing disease. For dementia with Lewy bodies, it's GBA, galactocerebrosise mutation. And so this is an enzyme that handles a type of sugar molecule in the brain, or a fatty sugar molecule. And so if you have a GBA mutation, you're at a higher risk for developing DLB or Parkinson's disease. But it's not absolute. So if you have 2 copies of that mutation, you get an entirely different disease called Gaucher's disease, which is very common in people of Eastern European and Ashkenazi Jewish descent. But if you have 1 mutation, it seems to increase the risk, but is not a guarantee that one will develop it.
Great, thank you. We have several questions about monoclonal antibodies and about alpha-synuclein, targeting alpha-synuclein. So I think that the main sort of theme of the questions here is, why are there no, or are there any monoclonal studies of monoclonal antibodies that target synuclein protein clumps?
There are. They're in very, very early stage. So you haven't heard about them because they haven't gotten very far in the process yet, right? The other thing is that the relative burden of synuclein in the brain is much, much less than the burden of amyloid or tau. So it's a harder target to get to. So you will see some trials down the road that are doing this. There are companies, the same companies that have developed the anti-amyloid and anti-tau antibodies are also working on anti-synuclein antibodies, but it's much, much farther down the road, very, very, very early phase studies. So it'll be a while before we really see one of these in a phase 2 study.
So you mentioned measuring synuclein in the body with cerebrospinal fluid. This is through a spinal tap and also through skin biopsy. So a couple of questions related to that. The first one is, are either or both of these tests available commercially today? And are they widely used in clinics? Or are they really mostly a research tool for now?
No, they're both available clinically. So the spinal fluid test is called the SYN-TAP. SYN-TAP, TAP, spinal tap. And the skin biopsy is called SYN-1, SYN, SYN-ONE. So they're both available clinically. They are CLIA cleared, which means they are clinical tests, and they meet all the requirements to be a clinical test. They're not covered by insurance for the most part. So the companies have developed some patient assistance programs to assist with that. The skin biopsy is really easy. It's an office procedure. I don't want to talk about one procedure over the other. It's a very easy procedure. It's done right on the exam table. It's about the size of it's smaller than the size of a pencil eraser. And so it's done very easy. My nurse practitioner does them all the time. The spinal tap requires a little bit more work because it's a spinal tap, but both tests are available. They're both available clinically. They're easily interpretable clinically, but they're not covered by insurance. But they're both easy to do for a neurologist.
Great, thank you. And I think we have time for sort of one more, let's call it a group of questions. We have several questions here about mixed pathology. And for those who are watching who might not be familiar with that term, what we're talking about here are people who have dementia for more than one cause, meaning they might have Alzheimer's disease and vascular dementia. They might have DLB and frontotemporal dementia. That would be less usual, but you get the idea. And then the questions are really related to how well might some of these drugs work in mixed pathology, people who have dementia from more than one cause, and with a specific example is, will Leqembi be made available to LBD patients who do not have an Alzheimer's diagnosis? I guess that's really more, that's less about mixed pathology and more about sort of other pathology.
Right. Yeah. So here's the thing, is that it's hard to answer a question for which there's no studies done to answer that question, right? So the studies are typically, so clinical trial has very rigorous criteria, right? And so to get into an Alzheimer trial, you need to have clear Alzheimer's disease without evidence of other diseases. To get into a DLB trial, you have to have clear evidence of DLB, right? And so in the Alzheimer trials, it's possible that some of them had DLB, but that wasn't specifically tested. And so we don't know whether these drugs would work or are safe in people with DLB. I think will be an ongoing area of investigation from the companies that make these drugs perspective. They literally just got approved for AD. So that's their focus at the moment, is to rolling it out to treat Alzheimer's disease. I think they do have an interest in whether this also would be effective in dementia with Lewy bodies, but that will require a study. And so it's going to be some time. So right now, for example, in our practice, we would not treat DLB patients with Leqembi or any of the other monoclonal antibodies because we have no evidence, one, that it would work, or two, that it's safe.
Great, thank you, Dr. Galvin. So it sounds like the answer to that question is, we really don't know yet, and until we do, it may not be a good idea to prescribe these things for people where we don't know the answer yet, and more research will help us clear that up. So thank you, everybody, for coming today and for all of your questions. Unfortunately, looking at the clock, we are just about out of time. So on behalf of LBDA, I would like to thank you all for your time and attention, and also thank Dr. Galvin for sharing his presentation and so patiently answering our questions. As a reminder, you will receive an email in about 1 week. That email will contain the link to the recording of the presentation in case you would like to share that with anyone. And we invite you to check out our calendar of events on the bottom of our homepage on our website. And now there you can find details for registration for any of our upcoming events, including more of these webinars. And speaking of, please mark your calendars for the next webinar, which is going to take place on Wednesday, October 5th at 2 p.m. Eastern Time. As a special treat to kick off Lewy Body Dementia Awareness Month, we're going to be offering in that webinar a special interactive movement presentation with David Leventhal from Dance for PD. And as a quick reminder, as you leave the webinar today, please do take a moment to complete the survey that will launch, because again, that does help inform our content for the future. And we hope to see you all again at the next webinar. Thank you very much.
Thank you. Bye-bye.
Thanks, Jim.